Take a look around you. I mean, really look. The device you're watching this on, the chair you're sitting in, the very air you're breathing. It's all just stuff, right? But how do we make sense of all this stuff? Well, today we're going to build a simple but really powerful system for classifying literally everything in the universe, just like a chemist would.
It's a huge question, right? But the answer starts with a single, simple word: matter. But, just calling everything matter doesn't really help us much, does it? That's kind of like having a giant library with all the books thrown in one big pile. To really understand the world, we need a system, a kind of flow chart for sorting all the different kinds of stuff that exists.
So, here's our game plan. First, we're going to pin down what matter actually is. Then, we'll sort it by its most obvious form. Is it a solid, a liquid, or a gas? After that, we'll dig a little deeper into what it's made of. Is it pure, or is it a jumble of things? And finally, we'll talk about the clues, the properties that help us tell it all apart.
Okay, first things first. Before we can start sorting all this stuff, we need to agree on what we're even talking about. And that means we have to start with the science that studies it all.
And that science is chemistry. Now, it's not just about bubbling beakers and crazy experiments. At its heart, chemistry is the science that asks three really important questions about everything. What's it made of? What makes it unique? And how can it change into something totally different? So, the star of our show today is matter. And the definition is actually super simple. If it has mass, meaning you can weigh it, and it has volume, meaning it takes up space, then congratulations, it's matter. A rock? That's matter. The air in your lungs? Yep, matter. But what about something like an idea or the light from your screen? Nope, no mass, no volume, not matter. Okay, so now that we know what matter is, let's start sorting it. And the first, most obvious way we classify things is something we do every single day without even thinking about it. We just look at what state it's in. Water is the perfect example here. I mean, we drink it as a liquid, we freeze it into solid ice cubes, and we can boil it into a gas we call steam. It's the exact same stuff, H2O, but it takes on three totally different forms. So, what's actually changing on the inside? And here's the answer. It all comes down to how the tiny little particles are behaving. In a solid, those particles are packed together in a tight, organized structure. They're basically just vibrating in place. That's why a solid holds its own shape. In a liquid, they're still close, but now they can slip and slide past each other, which is why a liquid takes the shape of whatever container you put it in. And a gas? Oh, it's total chaos. The particles are super far apart, zipping around like crazy, and they'll expand to fill any space you give them. All right, sorting things by solid, liquid, or gas is a great start. That's level 1. But now we're ready for level 2 of our classification system. We're going to stop looking at the form of the matter and start looking at its fundamental makeup. Is it one single thing, or is it a jumble of different things all thrown together?
And this flowchart right here, this is our roadmap for the rest of the way. You can take any substance in the universe and figure out exactly what it is by answering just a few simple questions. And the very first question we have to ask is right there at the top. Is this stuff the same all the way through?
That one question splits all matter into two giant categories. If the answer is yes, if every single tiny particle is exactly the same, like in a glass of pure water, we call that a pure substance. But if the answer is no, then what we have is a mixture. A cookie is a great example. Every bite is a little different, right? Its composition isn't uniform at all.
Okay, so let's follow that pure substance path first. We know it has a definite, uniform composition. But the next question is, can we break it down into something even simpler using a chemical reaction?
And the answer to that question gives us our next split. If you can't simplify it anymore, you've hit the end of the line. That's an element, like gold. But if you can break it down, like how we can split water into hydrogen and oxygen, then what you have is a compound, which is just a substance made of two or more elements that are chemically stuck together. So think of it like this. The elements are like the basic Lego bricks of the universe. You can find them all on the periodic table. Compounds, then, are what you get when you start snapping those elemental Lego bricks together, like combining hydrogen and oxygen to build water, or carbon and oxygen to build carbon dioxide. Okay, so that's the whole pure substance side of our flowchart figured out. Now let's jump back to that first fork in the road and go down the other path, mixtures. When we have a mixture, we have to ask a different question. How well are the ingredients actually mixed together? Is every spoonful going to taste the same? If the answer is yes, if everything is blended together so perfectly that you can't see the different parts, then you have a homogeneous mixture. You might also hear this called a solution.
But if the answer is no, if you can easily see the different components, like in a salad, then it's a heterogeneous mixture. And food gives us the best examples for this. Sweetened tea or apple juice are homogeneous. Once you stir in the sugar, you can't see it anymore. It's the same all the way through. But look at salad dressing. You can literally see the little blobs of oil floating around in the vinegar. And a chocolate chip cookie is the classic heterogeneous mixture. One bite might be mostly dough, and the next is a big chunk of chocolate.
And there you have it. We've basically built our entire classification system. But now the question is, how do we actually use it? How do we tell all this stuff apart in the real world? Well, we do it by observing its properties, the unique set of clues and characteristics that every substance has. Now, properties basically come in two main types. A physical property is something you can observe or measure without changing what the stuff is. For example, ice melting is a physical change. It's still H2O, just in a different form. But a chemical property describes its potential to become something new. You can only know that wood is flammable by actually burning it, which, turns it into ash and smoke. You fundamentally changed it.
And there's one last really important distinction. Does the property change if you have more or less of the stuff? If the answer is no, it's an intensive property. The boiling point of water is always 100 degrees Celsius, whether you have a tiny cup of it or a whole swimming pool. But if it does depend on the amount, like mass or volume, it's an extensive property. And here's why this matters so much. Scientists use intensive properties like density and melting point as fingerprints to identify unknown substances.
So, when you really get down to it, everything we've talked about, from solids and liquids to mixtures and compounds, it all comes back to this one powerful idea. The way those tiny invisible particles are structured and how they behave is what determines everything we can see and measure in the world around us. It's the ultimate link between the micro and the macro.
So I'm going to leave you with this thought. The next time you look at a simple glass of water, think about what you're really seeing. Yeah, it's a liquid, but it's also a pure substance. It's a compound made of two different elements, and it has a whole list of physical, chemical, intensive, and extensive properties. It's an entire universe of chemistry right there in the palm of your hand.